Now, okay, then we have seen the linearly dependent and independent vectors. Okay, linearly dependent and independent vectors. Okay, then we have seen that if S is a 1 0 1 0 1 0 0 0 1, okay, is a linearly independent set. Or we can say that these vectors are, okay, this is equivalent saying that, okay, this set is linearly independent set, or we can say the vectors are linearly independent. Zero, zero, one are linearly independent. Okay, this is equivalent saying. And we have also seen another example. If we say that, actually the definition is if they are linearly independent, if V1, V2, Vn are linearly independent, then okay, we will have then the linear combination. Okay, then the linear combination V1, V1, V2, V2, Vn, Vn equals to 0 will imply that C1, C2, Vn all are 0. Okay, so this is actually, it will be unique solution. After solving these equations, we will have unique solution for linearly independent case. But if they are linearly dependent, then this linear combination to 0 will from this linear combination, if we solve this equation, okay, after solving these equations, we will have actually the definition is, okay, if they are linearly dependent, then at least one Cj will be non-zero, not all 0. Okay, not all Ci, V1, C2, Cn are 0. Okay, some of them may be 0, but at least one will be non-zero. So that is the idea of linearly dependent set. Okay, for given vectors, V equals to 1, 1, 1, V2 equals to 2 minus 1, 4, V3 equals to 5, 2, and 7. Okay, in the last class we have seen that C1 will be 3, C2 will be 1, and C3 it is was minus 1 for the choice of C2, because we have selected C2 equals to 1. If we had selected C2 equals to some other thing, 2, 3 or something else, then we would have some different coefficients, okay, different values of CUIs, C1, C2, and C3. So that means after solving this linear combination equations, okay, from this linear combination we will get a system of linear equations. After solving it, we will get unique solution in case of if they are linearly independent. But if they are dependent, then we can see that there will be more than one solutions. Okay, at least one of them are non-zero, and for different choice of this one, we will have this situation. Okay, so okay, after this we have discussed in the last class. So today we are going to start on, we will look some more examples on linearly dependent and independent. Okay. Regarding this linear dependence and independence, one fact is there. Fact one is saying that a set of vectors containing zero vector is linearly dependent. Now suppose S is a vector, v1, v2, vn, and also this zero vector is also in there. Then if you take the linear combination 0 v1 plus 0 v2 plus assume some k not equals to 0 and k belongs to some real number. One scalar you are taking. Okay. So 0 vn plus k into 0 vector. So if you take the linear combination, okay, then from here what we will get? At least one k is non-zero. Okay, so whenever a set is containing zero vector, then the set is linearly, okay, S is linearly dependent. Now, any superset, fact 2, any superset of a linearly dependent set is also linearly dependent. Okay. Okay, the meaning of linearly dependent set, two vectors are linearly dependent if two vectors are linearly dependent, then one is a multiple of the other vector. Now, if you say take vector A as 1, 2, 3, 4, okay, and B is equal to 2, 4, 6, and 8. Then we can write B equals to 2 with 2A. So if we take the linear combination, so 2A minus B is equals to 0. So if we consider this type of linear combination and if we solve it from here, C1 is 2 and C2 is minus 1. Okay, so since they are linearly dependent, we are getting that coefficients are non-zero. Okay, the definition is at least one of them is 0. Okay, all can be non-zero. So here we are seeing the two coefficients C1 and C2 are non-zero. Okay, so if you take S1 as 1, 2, 3, 4 and 2, 3, 4, sorry, 2, 4, 6 and 8. Okay, any superset, since we know this set is linearly dependent, okay, now if you add one more vector, okay, which becomes a superset of this, suppose 3, 2, 1, 4, okay, then this S1 is also linearly dependent, is also linearly dependent set. Okay, so that is the meaning of this fact 2. Now there is a fact 3 also. Okay, any subset of a linearly independent set is also linearly independent. Now, if you go back and look back that suppose B, we have taken 0, 0, 0. One linearly independent set 0, 1, 0 and 0, 0, 1. We have seen, okay, if you want to verify this one. Then if you take any two sets, this vector 1 and vector 2, okay, then what will happen? Suppose B1 is a collection of B1 and B2. Okay, by this fact 3 is also linearly independent. Why? If you go, if you take the linear combination of these two vectors, C1 into 1, 0, 0 plus C2 into 0, 1, 0. So we'll get C1 equals, this 0 is actually 0, 0, 0, 0 vector actually. Since we are taking combination, linear combination of vectors. So it can be written as C1 is equal to 0, and which is C2 is also equal to 0. So from any linearly independent set, if you take any part of that, okay, any subset, that is linearly independent also. Okay.
Sir, may I speak something?
Yes, that's
Sir, that can be also be linearly dependent, no, sir. If C1 equals to 1 and C2 equals to 0, C2 equals to -1, maybe. Am I missing
oh,
something here?
oh, which one you are telling?
Fact 3, sir, example, the subset.
Okay, subset. No, no, if you take here from here. So if here from here, what you will get? C1, 0. Let me write first. Okay. Uh,
Sir, I think I understood my mistake. You can proceed, sir. I think I understood my mistake.
you got it?
Yes, sir, I got it.
Okay, let me explain. Okay, the thing is, we are selecting only two vectors. Okay, C1 into 1, 0, 0 plus C2 into 0, 1, 0. We are taking this linear combination. So this is actually 0, 0, 0. Okay. So if you take the linear system of linear equation, so you write it. Okay, this row vector is can also be written as column vector. C2 0, 1, 0, 0, 0, 0. Okay, from this, what we will get? C1 plus 0 C2. Okay, 0 C2 equals to 0. Then 0, 0 C1 plus C2 equals to 0, 0 C1 plus 0 C2 equals to 0. So this will give you C1 equals to 0, and this will give you C2 equals to 0. Okay. So they are linearly independent. Any subset of the linearly independent set is independent. Okay. So let us move to the next theorem. Since it is very difficult, because if you check this example, okay, let me write one more example. That the vector is set of vector. Okay, S is 4, 3, 2, and 2, 1, 4, and then vector 3 is 2, 3, minus 8. Okay, minus 8. So if you use the definition, whether it is linearly dependent or independent, if we want to check, so what we do, we write down C1 into P1. We can write it like this way: 4, 3, 2 plus C2 into V2. 214 plus C3 into 2, 3 minus 8 is equals to 0, 0, and 0. The 0 vector. Also remember here I want to mention that the row, okay, 1 cross in. Suppose we are having a vector v, v1 is equals to a11, a12, and a1n, 1 cross n. We call it row vector. Okay, just like row matrix, we call it row vector. Similarly, v2 will be called a21, a22, a2n. Okay, this will be called column vector. Okay, so this is from here what we'll get 4c1 plus 2c2 plus 2c3 equals to 0, and then 3c1 plus c2 plus 3c3 equals to 0. Again 2c1 plus 4c2 plus, not plus, this is minus, 8c3 equals to 0. Okay, so here we see a system of linear equations, a system of linear equation, a homogeneous system of, okay, homogeneous system of linear equations. Okay, by Cramer's rule, we have to check whether the determinant is 0 or not. If it is 0, then the system is consistent, but it will have infinitely many solutions. So let us take the determinant. Okay, the determinant is, okay, D may be the determinant. So 4, 2, 2, 3, 1, 3, and then 2, 4, minus 8. So if you take the determinant, what will happen? 4 minus 8 minus 12 minus 2 into, this will go, we will have minus 24 minus 6 plus 2 will be there. Okay, 2 is there. So now it will be, we will have 12 minus 2. So finally what we are getting? 4 into minus 20 minus 2 into minus 30. 30 plus 2 into 10. So finally you will get minus 80 plus 60 plus 20. So it is 0. Since the determinant is 0, so we can say that this system of homogeneous system of linear equations will have infinitely many solutions. Okay, if this vector, this set of vectors is linearly independent, okay, since it is dependent, so we are getting infinitely many solutions, more than one solutions we are getting. But if it was supposed to be linearly independent, then we will have C1, C2 and C3 as 0. Okay, since it will be very difficult if we have a order of 4 vectors are there, 5, then the determinant will be symbolic computation will be not symbolic, even if it is real numbers. Okay, it is very difficult to evaluate 5 by 5. Solving a 5 by 5 equation is very difficult. So the next theorem says, okay, by definition we can go and check whether it is linearly dependent or not. Now there is another shortcut method. Okay, this method says, it is actually a theorem. Okay, it says, consider a vector, a set of vectors. Okay, suppose S is given like this way, V1, V2 and Vn, where V1 is n tuple. Okay, n tuple. having n components. V2 is also example. So this actually Vi, V1, V2, and Vn are actually member of Rn. Okay, in the vector space. Then what will happen? It says, the theorem says, this set is linearly independent if and only if the determinant, okay, the determinant is non-zero. Okay, if we can show that the determinant is non-zero, then we can directly call that the given set of vectors is linearly independent. Now, the meaning of if and only if I will explain. If and only if actually, if this person holds, okay, then we will get this result. Again, if this portion holds, then we will get this result. Okay. Sometimes in brief it is called if and only if, IFF, or it is implies and implied by. In this way it can be written. Now let me write down one problem. Okay. The problem is, okay, find A so that the vectors 1, -1 and 2, 0, k and 3, -1, 2, 3 are linearly dependent. Okay, are linearly dependent. So what we'll do? Our task is to calculate the determinant with the and make it 0. Because if they are independent, then it will be non-zero. If they are dependent, then it will be 0. So that means we have to take the determinant 1 minus 2, sorry, 1 minus 1, 2, 0, k, 3, and -1, 2, 3. So we have to take the determinant exponent. It will be 0. So this will give us 1 into 3k minus 6 minus plus, or we can write it -0 plus -1. Okay, we are writing this way. So this is actually -3 minus 2k. It is 0. So what we are having, 3k minus 6 plus 3 minus and minus plus 2k. Okay, so it is 0. So finally we are having 2k, 3k. So 5k and -6 plus 3, so 3. So k equals to 3 by 5. Okay. If k equals to 3 by 5, then these vectors are actually linearly dependent. Okay. Now similar type of example can be given, that find the value of x so that for which particular value a given set of vectors will be linearly independent. Okay, if it is not supposed to be like this way, then we had to select non-zero. If we have to set independent, okay, independent, then we would have selected this way. Anyway, or some other example we can refer. Now there are a new, we are going to introduce one more definition, which is called generator or spanning vectors. Generators or spanning vectors. Now, if you remember the real number, the R2, the two-dimensional space. Okay, here we have seen that any vector, suppose any vector is given x and y, can be written as 1 0 plus y into 0 1. This is called a linear combination. Linear combination. Given any xy, we can represent this xy in terms of these two vectors, 1 0 and 0 1. For example, 1 comma 2 can be written as 1 0 plus 1. So these two vectors, okay, given any vector, we can written as these two vectors as a linear combination of these two vectors. Okay. For any other vectors from here, okay, we have to select some minus, okay, some negative numbers also. Then, so the definition says, similarly, if we consider about the three-dimensional space, okay, then any vector can be written as x, y, z is any vector. It is a linear combination of these three vectors. Okay. If we go in the four-dimensional space, fourth dimension, we cannot draw it. So let me write down. Okay. So any vector x, y, z, and w can be written as x 1 0 0 0 plus y into 0 1 0 0 plus z into 0 0 1 0 plus w into 0 0 0 and 1. Okay. So we are taking a particular some special vectors will be there. Okay. So that any vector can be written as a linear combination of these four vectors. Okay. Normally we call it standard identity vectors actually. Okay, we will be denoting as E1, E2, E3, and E4. So here E1 means 3 tuple. Okay. E3. So this is E1 and in E2. Okay. Similarly, we will be defining that E1 is 1 0 0 0. E2 is 0 1 0 0 and so on, and En 0 0 in the real number n dimensional space. Okay. Now let us come back to the definition. The definition says, let V be a vector space and V1, V2 and Vn be n vectors of the vector space. Then, and also we assume S is a subspace of V. S may be equal to V also. Okay. If every element of S can be expressed as a linear combination of these vectors, then we say that V1, V2 and Vn are generators of S. Okay. Are generators of S. That means and that is called the span of these vectors is actually equal to the S vector, the whole set. Okay, just if you think about this two-dimensional case, that the span of these two vectors, okay, 0, 1 and 1, 0, give any vector, we can write it as a linear combination. Take any vector as a linear combination. Okay, so that means this whole point, okay, the whole two-dimensional space can be represented in terms of these two vectors. Okay, this E1 and E2. In other words, the span of these two vectors, the span, okay, they can be expanded to the whole space. The span, the range of these two vectors, it will be, okay, these two vectors will generate the whole two-dimensional space. Okay, so in this definition, we can write a span of 1, 0 and 0, 1 is actually the two-dimensional space R2. Similarly, we can write the span of these three vectors. This is called spanning set actually. 0, 1, 0 and 0, 0, 1. This is R3. Similarly, span of E1, E2, E3 and E4 will be the four-dimensional space. Okay, so that is the meaning of generator. Okay, generator, why we are saying that generator, that any vector can be generated by these four vectors, okay, in four-dimensional space. In four-dimensional space, in three-dimensional space, okay, any vector can be generated by these three vectors. Similarly, in two-dimensional space, any vector can be generated through these two vectors. So that is the actual meaning of generator or the spanning vectors. Now, the question is, okay, so here what we see, V is actually our three-dimensional space, this one. Okay, now S is a subspace. S is given as x, y, 0, such that x and y belongs to the real number. X and y are real number. Then any x, y and 0 can be written as 0 into, okay, okay. Let me just write it down properly. So for this case, we don't need to write this one. Okay. So for this set, okay, span of 1, 0, 0 and 0, 1, 0 is actually this. These two vectors is sufficient to represent this, the elements of this set. Yes. Okay. So a span of this. So this is actually span of the set. Okay. Now there will be a definition called basis. Okay. So what is a basis? Basis, let V be a vector space. A vector space over the field of real number. Whenever we say V is a vector space, that means it has two operations. Okay. Over field of scalars, over the field of scalars R. Then a set of vectors V1, V2, Vn is said to be a basis of V if V1, V2, Vn are linearly independent and they generate V. And if they generate V, that means it has to satisfy these two equations, these two conditions actually. Span of V1, V2 and Vn is equals to V, then and V1, V2 and Vn are linearly independent. Okay. From this, remember the basis. It's very important idea of linear algebra, basis. Okay. It is two conditions of span. It will be a basis is a spanning set and second condition is linearly independent. It is linearly independent. Now, if you think about the basis for two-dimensional space, then what will have? B equals to 1, 0, 0, 1. It is linearly independent, we have seen it. And any vector, given a vector B, then we will see that the determinant is equal to what? Non-zero. So linearly independent. Okay, the vectors are linearly independent, and for any vector V belongs to the vector space, we can write as a linear combination of these two vectors. So that means, okay, so this implies span of 0 and 1 is actually a two-dimensional space. Similarly, we can see if it is R3, R4, and so on, Rn, okay, n-dimensional space. Similarly, we can show that. Now, the question is, this particular basis is called a standard basis. Or R2. Okay. Then standard basis for Rn will be standard basis for R3 will be R3 is 1, 0, 0, 0, 1, 0 and 0, 0, 1. Similarly, for R4, we can define for R4 and R5. Now, why we are selling a standard basis? Because a vector space V, okay, V plus dot can have more than one basis. We'll see in the next example. Now, the task is to verify whether it is a basis or not. Suppose V1 is another collection of vectors, is a set of vectors, then we can show that V is linearly independent. For this, what we need to do? 1, 1, 0, sorry, 1, 1, 1, 1, 1, 0, and 1, 0, 0. Let us take the determinant. Determinant will be I think it is, there is a mistake. Of 1, 0 minus 0, minus 1, of 1, of 1, that is, no, let me just write down. While we're taking this one, then this 0, 0 minus 0, minus 1 into again 0 minus 0. Plus, when we take this one, zero minus 1. So this is actually minus 1, non-zero. So they are linearly independent. Okay, the vectors are linearly independent. Now it is task to show whether we can write it. Any vector can be written as this form. That is span of 1, 1, 1. Whether it is true or not, we have to check. Is equal to R3 or not, we have to check it. Okay. Okay. If you write it down, suppose x, y, x1, any vector x1, x2, and x3 belongs to R3, then it can be shown. It is an easy task. That x1, x2, and x3 is x1 into, sorry, x3 into plus x2 minus x3, that is second one, 1, 1, 0, plus x1 minus x2 into 1, 0, 0. Okay, any vector can be written as in this form. So this implies that this equation is true. So it is true. Okay. Since we can write any vector from R3 in terms of these three vectors, so that means this relation is true. And we have already seen this is linearly independent. So this set, given set V1 is actually another basis for the real numbers the three-dimensional space R3. Okay. In fact, is a basis. Is a basis for R3. In fact, any a vector can have infinitely many bases. Okay. We may find some B1, B2, B3 in a different setup, so that we can show there also we may have some different other set B2, B3, which are also basis of this three-dimensional space. Okay, and this is true for all the vector spaces, not only at R3. Okay, we can find multiple bases for R4, R5, but there will be on standard basis. Okay, the standard basis is standard basis. Okay, one standard basis will be there. E1, E2, En. Okay. Now the next thing is, okay, it is just writing. Okay, so there is another non-trivial, okay, non-trivial vector space. This is a non-trivial vector space. Suppose V is the set. We are calling this V as M 2 by 2 matrices, collection of 2 by 2 matrices. A, B, C, and D. Okay, take the set as collection of matrices. Then A, B, C, and D are real numbers. Okay. Then we can show that this vector with matrix addition and matrix multiplication is a vector space over the real number set, over the field of scalars, the real number. Okay. Now it has a basis. The basis for this particular vector space is 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, then 0, 0, 1, 0, plus the final is 0, 0, 0, 1. Okay, because any vector, any matrix, any vector in this vector space is actually a matrix. Okay, C and D can be written as these four vectors. Okay, a linear combination of these four vectors. And we can easily show this is a, okay, this is a linearly independent set. Take this C1 into this one, 1, 0, 1, 0, 1, plus C2 into 0, 1, 0, 0, plus C3 into 0, 0, 1, 0, plus C4 into 0, 0, 0, 1. Okay, this linear combination 0, 0, 0, 0. The zero vector in this matrix space, in this vector space is actually 0, 0, 0 matrix of order 2, order 2 by 2. So any vector can be written as of these four vectors. Okay, in the matrix actually. Plus B, C into plus D into so this is actually a basis for this matrix space. Okay, a basis. The basis of this vector space M 2 cross 2 matrix. Okay, so this is another actually non-trivial example of a basis. Now the task is to whether it is basis or not, it is your task to verify. Okay. Well, the question is yes. You just have to show whether, okay, the task is to show the determinant is non-zero. 0, 1, 1. Determinant is non-zero and span of this 1, 0, and 0, 1, 1 is equal to the real number set, real number, three-dimensional space. So that means any vector, you take any vector x, y, z. Okay. So you have to find out some suitable C1, C2, and C3, so that you can write it as a linear combination of 1, 1, 0 and 1, 0, 1, 0, 0, 0, 1, 1. Okay. You just have to find out this Ci, C1, C2, and Cn. Okay. If it is linear number, if they are real numbers, then you can. Okay. It will be a real number. Okay. Just find out the real number so that you can write it. If you can do that, then you can call it that this B is also a basis. Okay, basis of R3. That is a standard basis. Okay. Now there is a theorem which is called replacement theorem. Okay. What it says, I think I will stop here today. If you have any doubt, please ask.
Sir, I have a doubt, sir.
Yes, tell.
Sir, for checking spam, is there any other mathematical condition like the one we use now? A better.
For a spanning set, whether it is a spanning set or not, we just have to do it. That whether any vector from the vector space, okay, can be represented in terms of the other vectors, that the given set of vectors.
Like
That is the only way, actually.
Only way, yes.
Yes. For checking the spanning, whether it is a spanning set or not, you have to do it. That's how it is way. For linear independence, we have the determinant factor. Okay, whether we can, from the linear combination, we are making it a 0. Whether it is the all Ci are 0, then we can say that this is a linear combination. I mean, linearly independent. It is a shortcut method to find out the determinant. Okay. But for computing this, whether it is spanning or not, we have to take any arbitrary vector from the vector space, and we check whether it is possible or not to represent in terms of those particular vectors that is given to check whether it is basis or not.
Thank you, sir.
Yes, a standard basis. There is a question. Standard basis is always since remember standard basis are always span vectors. Actually, the answer is within your question. Whenever you are calling it is a basis, that means it is already a span. Okay, a spanning set can be not a basis. There are vectors that can span the vector space or a subspace. Okay, but they may not be linearly independent. Okay, the identity vectors only a standard basis. A standard basis, that is why it is called a standard, because we have more than one vector, I mean basis. So we have to have one particular standard. Okay. The third question is, can we say all linear dependent vectors can be linearly independent? No, we cannot do it. Okay, the question is, what is the role of basis of a span vector? The role of, okay, let me first try answer this question. What is a standard basis? Standard basis, it will be like unit vectors will be there.